we ran into quantum optics and learned a little bit about quantum optics in my group from running into her talks online. And I hope that this is an opportunity for us to contribute another talk that we can also put online for the benefit of others. Because the talk that Maria organized before, also before Corona, were I think very useful and illuminating for people going into the field. And then later on, we had Peter Homeloff, also from Erlangen, suggesting we contact Maria for research. We have some people connecting who are unmuted them, so I'll mute them along the way. Don't feel bad about it if I'm muted, just to be safe. So Peter also recommended we contact Maria in context of projects we're working on. And we had a couple of discussions over the last several weeks that were extremely useful for us. And I thought it will be a good opportunity to invite Maria more formally to present at the Technion in the Quantum Center to give a tutorial. And I want to do it in a way that will be both available and open and give us opportunities to ask questions. And also go further and deeper into topics that Maria is an expert on and is a leader in those topics. So we will have two parts to this meeting. The first part will be more introductory in quantum optics, and please feel free to ask questions. And then we'll take a break and go to the second part that will go deeper into ultrafast quantum optics with higher, brighter sources. This is a topic that I think is extremely interesting, and Maria is a leader in this area. Also present her work. I think in both parts we are interested in asking questions, and for anyone who's here, students or faculty, feel free to interrupt and ask questions. I hope this can be an interesting discussion. And if we see that we're running a little bit over time, I'll let it go. If we see that we run really over time, much of the time, I'll try to limit it. But generally, we'll keep it flexible. We're planning for about an hour and a half, and with some break in the middle. With some short break in the middle that can also be useful for discussions. Also happy to see researchers and faculty members from around Israel. And I know that Maria is also collaborating with many people here that I only learned about it after we contacted you, thanks to Peter's advice. I'm glad for that. So I think I'll give the stage to Maria. We'll start the talk. Thanks, Maria, for coming.
Thank you, Ido, for introducing me. A little bit correction. My talk will indeed have two parts, but the break will be between the part about weak non-classical light and strong non-classical light. And again, please stop me and ask questions if something is not clear, because I'm not going to teach you quantum optics. I'm going to teach you all about parametric down conversion, so to say, and it's not easy to squeeze in 1 hour. So let me share my screen. Yeah, do you see my screen?
Yes.
Okay.
Well, okay.
I will also get some laser pointer. So I'm indeed from Max Planck Institute for the Science of Light in Erlangen, Germany, and this is where it is. This is Germany. This is Erlangen, a little bit north of Nuremberg, which everybody heard of. And our institute is here. It looks like this, very nice building. It's only 3 years old. About that, and it's very nice. My group in this institute is called Quantum Radiation Group. It's a very small research group, and if you're interested later, I can tell you briefly what we are doing other than what I will mention in this talk. So this is my overview, my plan. First, I will introduce parametric down conversion, and I will use some theory. I will use some formulas. So please, if it irritates you, let me know. I know that some people prefer pictures to formulas, but I will indeed use some formulas. And then the two parts. One about weakly pumped parametric down conversion, and in this case it emits so-called biphotons, photon pairs, and I will try to explain what is quantum, non-classical. Non-classical in quantum and quantum in my talk will be synonyms. And so when I say non-classical, I mean something that is not described by classical theory of light, classical optics. And then bright squeezed vacuum is the second part. So what happens with parametric down conversion when we pump it very strongly, when it is very efficient? And between these two parts, there will be a break for questions, as Ido suggested. So parametric down conversion. Maybe all of you have heard that sometimes people generate photon pairs. So how it happens, a pump photon enters a crystal with quadratic second order nonlinearity and two daughter photons are emitted. They're called idler and signal for the reasons that I will explain a little bit later. And for these photons, we have the relations for their frequencies. The sum of their frequencies should be equal to the pump frequency. And of course, if you put h bar in front of the frequency, you will get the energy conservation. And of course, the wave vectors of the two photons should be equal to the pump wave vectors. And this is a momentum conservation if you put the h bar in front of k vectors. In terms of nonlinear optics, this is called phase matching, and it means that the nonlinear wave generated by the pump propagates with the same phase velocity, and there is energy exchange. But what can we say about this process? Sometimes naively it is explained like reversed sum frequency generation. When we do in nonlinear optics sum frequency generation, we combine two photons of frequencies omega s and omega I into one photon of a sum frequency. However, unlike sum frequency generation or second harmonic generation, parametric down conversion does not follow from the laws of classical nonlinear optics, and I will speak much about it. And the simple way to explain it is the noise of a parametric amplifier, which I'm going to pass to next. But this noise is a quantum noise. It's not really classical. It has quantum features. So what is a parametric amplifier? This is a box like this. It's a device known for more than 50 years now, probably. Yeah, about 50 years. And now this is a commercial device. You turn some knobs and you change the frequency at which it works, but let's see how it works. In principle, it is a device to amplify light. In an optical parametric amplifier, there is a nonlinear material. Typically, it's a crystal with a second order nonlinearity. You send the pump in, of course, to provide energy, and you send some signal beam. Here I show some yellow arrow, which means visible range, some yellow frequency, for instance, yellow wavelength, and it is amplified at the output. But from the beginning, everybody knew that also a second beam appeared that was called idler, just for this reason, because it is not useful, it's just idle. It's not doing any job. It was just accompanying signal, and it can be also interpreted as the difference frequency generation. In nonlinear optics, if you have pump frequency and you have signal frequency, then there is a difference frequency difference. However, people noticed, and that was actually great discovery, that even when you don't have the signal at the input, you still have at the output the signal beam and the idler beam. And this could be discovered by looking, yeah, questions?
Ego.
Hello? Should I continue?
Yes,
yeah, I think it's just people joining are not
yeah.
muted automatically. Yeah.
Actually, if someone raises hand or if someone writes in chat, I will not see it. So either Ido should tell me or someone should just speak up. Okay, so if you put an eye here, which you should never do from the viewpoint of laser safety, but if you look into all this, you will see a picture like this. So you will see colored rings. The angles correspond to wavelengths. This is, for instance, the situation for collinear degenerate type 2 parametric down conversion. The degenerate wavelength is collinear with the pump. And then there is something yellow, something more shifted to the blue, green and blue, and so on. And this was noticed in 3 groups simultaneously in 1967, independently. I'm very proud that later I was educated by some people from this 3rd group in Moscow. So how does it appear? Classically, this is impossible. So to explain it, I really have to write down the Hamiltonian. And to write down the Hamiltonian, I have to remember some nonlinear optics. In nonlinear optics, we have not only polarization of the matter is not only linear connected to the electric field, but there are also nonlinear terms related to 2nd order susceptibility of the material and 3rd order susceptibility of the material and further. In this talk, I will only deal with effects, well, one effect, parametric down conversion, that is based on this 2nd order term, which means that to provide this chi2, you need materials without center of inversion, center of symmetry. Some crystals have this feature, for instance, lithium niobate, barium borate, and other lithium niobate and so on. And then if this kind of polarization is present, then if we take into account the dipole interaction between the material and the field, so here E comes from the field and D comes from the material. D is the dipole moment induced in the crystal. And this dipole moment is just the integral of the nonlinear polarization over the volume, because the nonlinear polarization is by definition the density of the dipole moment. Then combining all this together, you have, roughly speaking, 3 fields, 2 from here and 1 from here. And you have Hamiltonian given by the integration over this crystal of the cube of the field and of the 2nd order susceptibility. And then if you assume that the field has 3 parts, first part is your pump that you send into the crystal, and the 2 other fields are quantum fields, because we know that even in the absence of a real light source that you feed into the material, there are vacuum fluctuations. There are 0-point fluctuations of the electromagnetic vacuum. And so from the viewpoint of quantum optics, vacuum is not just nothing. There is some vacuum field which you have to put here by hands and then assume that this field in the vacuum state or in some coherent state and so on. So this is basically, in terms of hand waving, how this interaction appears. You just plug the sum of the 3 fields here, take it to the power 3, and only take terms that have 1 pump field and 2 signal idler fields, and you will obtain this combination, the pump field. And because in quantum mechanics, fields correspond to photon creation and annihilation operators. Again, I hope that I don't have to explain such things, but yeah, I hope that people know what are creation operators. And then the Hamiltonian will have the pump field, which is classical. We don't need to write the annihilation operator, which we should if we describe it fully quantum mechanically, but the pump is so strong that I can assume that this is just a classical field, and then you get 2 operators. So far, from the very beginning, we don't know in which mode these operators are. There are all modes present in the vacuum, but only some modes will play some role in this game, because only for some modes, this phase matching relation will be satisfied in the end. And then if there is only 1 mode in the end that satisfies phase matching relation, and then the photon creation operator is a dagger for this mode, then the Hamiltonian will have this form. I will distinguish these 2 cases, non-degenerate and degenerate case. So here, the Hamiltonian creates pairs at in two different modes, S and I. They can be different frequencies, but they also can be different directions, or they can be different polarizations. And this Hamiltonian creates photons in photon pairs in the same mode. But because the Hamiltonian has photon creation operators, we can already sense the generation of photon pairs. So we further will explain how photon pairs appear. But let me first explain why this mystery, why nothing at the input, but something at the output. For a theoretician, I can say that this just follows from the photon creation and operators, creation and annihilation operators not commuting. A and A dagger do not commute in quantum mechanics, and this will lead to certain consequences. So I just show you how to derive a parametric down conversion signal, assuming this Hamiltonian. And here, note that here I dragged IH bar from the expression for the Hamiltonian. I don't care what else is contained here, but the rest I denoted by gamma, and gamma will be proportional, of course, to the pump field. According to my previous slide, you see there was pump field here, then there was chi2 because it was in the nonlinear polarization, and then there will be length of the material. I didn't derive it, but you can guess. Of course, the more material I take, the more the stronger interaction my interaction is. And so what I have to write here, well, there are different approaches. I can describe it later if you want in more detail, but there are two options to use Heisenberg approach or Schrödinger approach. In the Heisenberg approach, I'm interested in the evolution of the operators, and I assume that the state is the same. In the Schrödinger approach, on the contrary, I describe the evolution of the state and assume the operators to be the same. The result is not changed by what approach I choose, but here I want to show you the Heisenberg approach, and it is based on the Heisenberg equations, which are written here. The time derivative of an operator is related to the commutator of this operator with the Hamiltonian. And then I write this for signal and for idler and substitute the commutators, which is easy to calculate, and I get the result, which is known as the Bogoliubov transformations. Actually, it's a very broad, these transformations have a very broad range of applications. For instance, they are used in superconductivity, for instance. But here they are describing parametric amplification, and you see the output signal operator, photon annihilation operator for the signal mode is related to the input operator for the signal mode and the conjugated input operator for the idler mode. U and V are cosine and sine, hyperbolic cosine and sine of this gamma, this interaction constant, interaction parameter, integrated over time. Actually, it should be integrated over time, but here I just multiplied it by the typical time of the interaction. This is a very weird thing. What is meant by this tau, t? I can assume that this is the pulse duration, roughly. This is the pulse duration if I use pulses. And so there is this transformation from input AS and AI to output AS and AI, and then I can calculate everything using these transformations. And the recipe is simple. I take the operators here and I average it over the initial state, because I assume in the Heisenberg approach that the state is not changed. It's the operators that evolve. They evolve like this. And then I calculate the mean photon number, for instance, if I want, in the signal mode, suppose, AS dagger AS, and the averaging is over the initial vacuum state. And here it goes. I just plug these Bogoliubov transformations into this mean value. I get 4 terms here, of course, because it's 2 by 2. And then there are some terms which will disappear after averaging over the vacuum state. And these are these terms, first, second, and third, because here the A dagger, A acts on the vacuum from left to right, tries to annihilate a photon in the vacuum, and the result is 0. Here, for instance, this term disappears because A dagger acts on the vacuum from right to left. And here again, AS acts on the vacuum from left to right. So these terms disappear. What remains is this term where I use the commutation relation. And just because the A and A dagger do not commute, I get this V squared because it will be 1 plus the normally ordered combination. And my result is that although the input number of photons in the signal mode, and of course in the ideal mode is 0, the output number of photons is hyperbolic sine square of gamma t, and gamma t can be large. So the output number of photons can be large, non-zero at least, with nothing at the input, and this explains the noise of the parametric amplifier. So in the next part of my talk, I will consider weak interaction. I will consider the case where this gamma t, and I would like to denote it by a letter G, and in the future I will call this parametric gain. It's a little bit ambiguous because some people call parametric gain the amplification of the incident wave. But for me, it's important to call something this value because depending on whether it's small or large, everything changes. And so this parametric gain will be, as I said, scaling with the pump field, with the susceptibility, and with the length of the crystal and with the time of the interaction. At small parametric gain, I can use Schrödinger picture. So I will not use this approach I described you here. I will take the Hamiltonian and derive from the Hamiltonian the state that is evolving, that is appearing. And the equation, I will use the Schrödinger equation. And this is the solution of the Schrödinger equation. In quantum mechanics, this is called the evolution operator. I have to integrate the Hamiltonian over time, divide by IH bar, and that's why I dragged IH bar from the Hamiltonian. And then I act with this evolution operator on the initial state, psi at 0, and psi at 0 is the vacuum. So I do this, I plug the Hamiltonian. Integration over time just gives me multiplication of this gamma by t, and then I get this exponential function. And then, of course, if the g is small, I can expand it like this, do the Taylor expansion for this exponential, and I get that mainly I will have the vacuum, but then with a small factor here, g, I will get a state where one photon is in the signal mode and one photon in the ideal mode. These are called single photon Fock states. I guess you know what Fock states are. In any case, I don't have time to explain, but these are Fock states in two mode Fock states of pair states, photon pairs, and these photon pairs are called biphotons. So now I will smoothly switch to my second part, after which I will make a break, and the second part will go without a break. Although I think I spent already 20 minutes, but the second part will be shorter. The bright light part will be shorter. So let me use another 15 minutes at least for this biphoton part. So why these photon pairs are interesting and important? First of all, they feature entanglement, and I will speak in much detail what is entanglement in time frequency, in position momentum, sometimes in polarization, and they're very useful in quantum information because of this. Then there is a nice method of producing single photons based on these photon pairs. I will not describe it further, but I will just mention now that if photon A is considered a trigger, so as it is registered by a detector, and then this detector releases the photon B also. So for instance, I send the signal to some gate, and after the photon B is delayed, I open the gate and I release the photon B, and I know that it's exactly one photon. So it's called heralded preparation of single photons, because this detector works as a, or this photon heralds the appearance of the other photon. And finally, in quantum metrology, these states are very important, basically because we know exactly when we know exactly the number of photons here, we know exactly the number of photons here. So it's used for instance, absolute calibration of single photon detectors. And there are other methods like quantum imaging, some kinds of quantum imaging, for instance, based on these pairs. Okay, so how do we detect these biphotons? Obviously, we need two detectors, and these detectors have to be sensitive to single photons. They are sometimes called click detectors, on-off detectors, or single photon detectors. And this detector gives at the output a click or a pulse when the photon hits it with some probability, which can be for very advanced detectors like nanowires, for instance, can be very high, can be 90% probability today. And so there are these clicks. And then after the detectors, I have something called a coincidence circuit. This is an electronic device that gives a pulse as soon as two pulses arrive simultaneously. Or today, time taggers are more used. These are devices that just record the arrivals of these pulses and analyze them, looking at the distribution of arrival times between two pulses. And what is important is the rate of coincidences, rate of simultaneous arrivals of these photons. For instance, these are coincidences. These two pulses and these two pulses are coincident. And these two and this do not have matches. And so we need the rate of coincidences, and then we need the rate of accidental coincidences. This is the rate. Yes? Question? Okay, no question. The rate of accidental coincidences is the rate of coincidences that would be if at the inputs of these two detectors were completely independent fluxes of photons, but with the same mean with the same rate, with the same flux. And then by dividing the number of coincidences by the number of accidental coincidences, experimentalists get what they call second order correlation function, G2. It's very important in measurements with photon pairs. But from the theoretical viewpoint, this G2 is defined as normalized, normally ordered second moment of the photon number. So I write here explicitly. So it's A dagger squared, A squared, divided by A dagger A squared. And this has to be averaged over the state. So for any state, there is this G2. You can calculate this G2. For instance, for coherent light, it will be 1. For thermal light, it will be 2. I will speak about this G2 in my second part, in the second part of my talk as well. But for a weak flux of photon pairs, so for SPDC photons, for photons generated by parametric down conversion, this G2 has this form. If you have a single mode, by the way, if there are more modes, it's a bit different. So 2 plus 1 over mean number of photons. And if the mean number of photons per mode, usually, is much smaller than 1, then this G2 is much larger than 1. And people observe very high coincidence peak. Now, what is entanglement? Well, the story started very, very long ago. I'm not going to go into the whole history of the event, but I showed the 3 pictures of Einstein, Podolsky, and Rosen, who wrote a paper in PhysRev in 1935. By the way, Podolsky and Rosen were PhD students of Einstein. That's why here they look a little bit old, but then probably they were a little bit younger. And they considered a Gedanken experiment, a thought experiment, which led to some paradox, which again, I don't have time to describe in detail how it was formulated and what was wrong in the assumption, because the quantum mechanics is complete in the end. But the paradox was as follows: that suppose that there is a source that generates pairs of particles. Actually, they consider the particle decaying into 2. So there is a mother particle and 2 daughter particles. And these 2 daughter particles, A and B, start to fly in 2 different directions. And they are at some point very far from each other. But there is correlation in positions of their birth and in momenta. Because initially, for instance, the mother particle didn't have a momentum p, but and therefore the sum of their momentums should be zero, and the difference of their positions should be zero because they are just created at one point. And then the paradox was that by doing measurements on one particle, and for instance measuring the position, we can infer the position of the other one, and while it is far away. And we could also measure position for one particle and momentum for the other particle and infer both simultaneously. That was the paradox. And such case was later called by Schrödinger actually entanglement. And it can be mathematically formulated as the wave function of the state vector of the whole system being not factorable into the state vectors of two subsystems. So such states are called entangled, and I'm going to show you how such entangled states are produced by parametric down conversion. And this is an exact counterpart of the paradox in the sense that we can speak about position and momentum entanglement. You know, in quantum optics, even now, very often people think that entanglement is only polarization entanglement, which is more commonly known, more famous. But here I want to speak about position and momentum entanglement, and the reason is that I have some interest in connection with those experiments. So there is a criterion of entanglement that was formulated rather recently, but it's very, very close to what Einstein, Podolsky, and Rosen considered, and namely the delta is an uncertainty. So uncertainty in the difference of positions for the two particles times the uncertainty in the sum of their momentums should be less than h bar, or better, much less than h bar. And this shows that it seemingly violates the uncertainty principle. So this is the so-called Mancini's criterion. And let's see how it works for parametric down conversion. Consider now this nonlinear crystal with second order susceptibility. We send a pump, this is the pump, and photons are generated in some directions. This is the non-collinear case where the k vectors are non-collinear to the pump k vector. So one of them, let's call the signal, can be generated in different directions. The spectrum of the angular spectrum of emission can be rather broad. But if the idler photon is registered at this angle, then there is only one direction or very narrow range of directions where you find the correlated signal photon. So you can introduce the total spectral range, angular range of emission, and the range of correlations. Typically, this total spectral range is much larger than the range of correlations. And this can be formulated like this. So one subsystem, let's say the idler photon is one subsystem, has very large uncertainty, but at the same time, there are very tight correlations between the two subsystems. If you find signal here, the idler can be only here. Now, of course, the angle of emission is in one-to-one correspondence with the transverse momentum. Here, theta is the angle of emission, p is the momentum, and the momentum for a photon is the same basically as its wave vector. And then the position will be the position where it emerges from the crystal. I will call it the transverse position, and this p transverse will be transverse momentum. And so you see the analogy. If I spoke about the uncertainty in the angle, it's the uncertainty in the momentum. And the uncertainty here in the position is, well, the same as in the paradox. So how it was measured? This experiment was measured by John Howell, who is also now in Israel as far as I know, but then he was in Robert Boyd's group. And they made a very nice, neat experiment. I will not describe the whole scheme, but this is a BBO crystal, beta barium borate, where they generated biphotons. And then they were biphotons of different polarizations, so they split signal and Adler in polarization. And then they looked in one setup, they looked at the near field, building the image of the crystal, optically building the image of the crystal on the detector or on a slit that they used to filter the position, the possible position of the photon. And then the other scheme just imaged the Fourier plane on the detector. So there was a lens, and in the focal plane of the lens, they looked at the photons. They looked for the photons. And as I said, they sent the photons to avalanche photodiodes. That's one example of single photon detector. And the pulses from avalanche photodiodes they sent to the coincidence circuit or to a time tagger, I don't remember. And they scanned one of the detectors or the slit in front of the detector and looked at the coincidences in both cases. And they measured the width of the correlations. So they measured exactly this Mancini's criterion. Delta x squared is the variance of the position where the photons are created in the crystal. And delta p squared is the variance of the momentum. And this was about 100 times less than the squared Planck constant, which showed the entanglement. A little bit, well, I'm already half an hour. Maybe I will need 10 minutes more for the first part. I hope it's okay. Is it okay?
Yeah, I think it's okay. Don't worry.
It's okay. Okay. So mathematical way to describe these correlations is to plot so-called two-photon amplitude. There are a lot of terms for this. I don't understand why people introduce new terms, but I think this was the initial term, and this is the probability amplitude that one photon, the Adler photon, is emitted at an angle theta I, and the signal photon is emitted at angle theta S. And the same you can draw for the position. So this is the probability amplitude that the signal photon is emitted at position xs and the Adler photon at position xi. And then you see that these distributions have certain widths. This total width along theta I, for instance, is called unconditional width because it gives you the total width of the angular spectrum. It's the projection of this, well, to be precise, the spectrum is the square of this amplitude, right? But roughly, this is the width of the angular spectrum. And then there is conditional width, and this is the width of the cross-section. This is what happens if you detect one photon, signal photon here, for instance, at this angle, and this is where its Adler counterpart can be. This is narrower. Delta small is narrower than delta large. And the same can be introduced for the position. And then these two things are Fourier related. Mathematically, if you just describe this generation of photons, then there should be Fourier relation, and the Fourier relation actually is like for the relation between diffraction, between the near field and far field properties of a beam. Of a light beam, and the transition from near field to far field is described by diffraction. So you can say that this is a two-dimensional diffraction. To pass from this figure to this figure, you just have to do the Fourier transform in 2 dimensions. And then there is some very simple algebra that shows that instead of measuring both in the near and the far field, you can measure only in the near field, but you have to measure the unconditional width and the conditional width. And namely, these Fourier transform features lead to the small delta x, this conditional width delta x, being related to the unconditional width in delta theta. And the other way around, the conditional width in delta theta is related to the unconditional width in delta x. This is just the consequences of the Fourier transform. And then this Mancini product boils down to this ratio of the unconditional width to the conditional width. But again, I did it in a very unprecise way, an inaccurate way. So this should be, and this, the width of the intensity distribution or the probability distribution, not the probability amplitude. And there is an issue there because the phase is lost. When you describe the amplitude and everything is nice, Fourier transform works, but when you go to the probability, then the phase of this amplitude disappears. And strictly speaking, this is not always correct, but it is correct if there is no, if you are really exactly in the near field and really exactly in the far field, then it is correct. And this led to the definition of another measure of entanglement introduced by Fedorov, and it is called Fedorov ratio sometimes, the ratio of the unconditional width to the conditional width. Now the same happens in frequency. The same entanglement happens in frequency or in frequency time or in energy time. The two photons have a restriction. They have correlation in their energy, in their time of birth. They are generated roughly at the same time, and they are generated with anti-correlated frequencies. I will show what it means in naive experimentalists' interpretation. So the signal and the idler photons have some spectrum. This is the idler spectrum, this is the signal spectrum. If you find the signal photon at frequency omega s, then there will be some small range of idler photons that will have correlation, will be correlated with this photon. So actually one photon, yeah, but this photon will have uncertainty in frequency only within a narrower range than the whole spectrum, than the whole frequency spectrum. And again, there is this unconditional width, delta omega, and there is the conditional width, delta small omega. And again, one can introduce this Fedorov's measure of entanglement, which is simple because you just need to measure the spectrum. You don't need to measure both time and spectrum. Again, I will not repeat this reasoning. You can introduce join two-photon amplitude in frequency, two-photon amplitude in time. They are Fourier related. The Mancini's measure is the product of the widths of the uncertainties in the sum of the frequencies and in the difference of the times. You see, in frequency there is anti-correlation, in time there is correlation. Also you can use Fedorov's measure. But in frequency, again, one should be careful because this is true, this measure works if there is no phase, frequency-dependent phase of this two-photon amplitude. So this two-photon amplitude is a complex number, it has a phase, and if this phase is not flat, then some of the entanglement, one can say some of the entanglement is in the phase, and this measure only retrieves the phase in the amplitude, in the intensity, in the photon number, so to say, yeah? I hope this is clear. I expect a lot of questions, but I'm ready to answer them. And it is always an underestimate. And I can explain again in a hand-waving way why it is an underestimate. Because it is like when you know the spectrum of light pulse, you cannot say that the pulses, that the pulse duration is always the inverse of the spectrum, because you can overestimate the pulse width. The same here. If you know this unconditional width in frequency, you can say that your conditional width in time here is at least larger than something. And so it gives you, in this Fedorov measure, it gives you the lower limit for entanglement. But there was an experiment recently where they measured both time and in time and frequency domains. So they were able to reconstruct this Mancini's measure. Why is it difficult? I forgot to mention, because while the frequency parameters are rather convenient. The width here, the conditional width here is about the spectral width of the pump. And if the pump is pulsed, it's easily measured. And this is is given by the crystal length and so on. So it's even larger and it's easily measured again. But this value, the conditional width in time, and also probably this value, are on the, well, this value is on the femtosecond scale. So it's very difficult to measure it. Using the detectors that have uncertainty of time measurement on the order of few tens at least of picoseconds. I think the fastest single photon detectors can resolve maybe 50 picoseconds, but not better. And this will be on the femtosecond scale, something like that. So what this group did, let me show you the next slide. So the group of Kevin Resch, I think, made this experiment where you see they have a nice picture. They can switch from frequency measurement to time measurement, how they did it. And this is what they obtained. This is the two-photon, now probability, because it's already square of the amplitude in frequency, omega signal, omega idler, and here in time. And here the values, it was difficult to see from the paper, but I put here the values just amplified. So the width, yes? Hello? Was it a question? No.
I think that people connecting
don't
always have mute on the microphone.
Okay. So the time scale here is picoseconds, sub-picosecond. And here the width of this distribution is about half a picosecond. So how did they measure? They used a very clever trick. They used up conversion of these photons by femtosecond pulses. So the up conversion happened and they detected the up converted photon. The up conversion happened only in the presence of the femtosecond pulse. And therefore the resolution, the time resolution was given by this femtosecond pulse. I find it completely fantastic measurement.
So that's the reason they are able to get spectrometry with time resolution on femtosecond timescales.
Exactly.
Or almost picosecond and below.
Yeah.
But how is it combined then with the spectral resolution?
Well, the spectral resolution, I think they just used the different detectors. I think they used how people measure these spectra. There are different techniques. One way is they put a monochromator here and the monochromator here, and they scan monochromators and measure coincidences. See, as simple as that. Another way is to put fibers here and here. And this is actually a very, very cool way to measure. We use it starting from long ago. The delay in the fiber is related to the frequency because the fiber has group velocity dispersion. And then you can do just time stamping, time tagging, and infer the frequencies. That's what is done usually now. But
so
I think
never a regular spectrometer, no grating. The fiber was actually doing the same thing.
Exactly. Yeah. Exactly.
Wow, that's really cool.
Yeah. And this is based on the fact that photons are correlated. So, for instance, you can just measure for a CW pumped source when the pump is a continuous wave, not a pulsed wave. You can just measure the delay between the two photons after a fiber, and you can infer their frequencies because you know that they are correlated. But for this method, for two-dimensional, for building two-dimensional distribution, you need to know the delay with respect to some trigger. And as this trigger, they use the pump. This is an interesting extension of this method. Yeah.
Still, you see the duration, even though the original source is not a femtosecond pulse. Is the original source driving the SVDC.
Few picoseconds. I don't remember what kind of source they used, but definitely a pulse, because this unconditional distribution in time is just a pulse duration where your photon can appear in principle, yeah, and it can appear within 2 picoseconds.
Mm.
So I think that
if you make a similar experiment with the CW, right,
it will be infinitely long.
Even though the two photons arrive at almost the same time. Okay, so it will be
the same time will be you will have just a very long, infinitely long line, and the width of this line will give you the relative the time difference between the arrival times.
So the width can still be on the scale of picoseconds, even.
Yeah, I think it will be. It can be. The width will be given by the inverse width of the spectrum, as I said, yeah. And the inverse width of the spectrum, I will talk about it in a minute.
Yeah.
Okay, so I will very quickly finish this first part, which is just the last slide I want to give, is the typical scales of correlations. Here is the geometry, typical geometry of experiment. This is the width of the pump, waist of the pump, and this is the length of the crystal. So, but the width of the pump now will be irrelevant for me, because the difference of the times, the uncertainty in the difference of the times of the two photons is given for these Fourier because of these Fourier considerations by the inverse unconditional spectrum. So the broader the spectrum of your SPDC, the tighter the photons are correlated to each other, no matter what the pump is. I mean, if the pump is very short pulse, then it's different. But typically, if the pump is picosecond, for instance, or 300 femtosecond, then it's the total width of the spectrum. And the total width of the spectrum, it so happens, it's not very easy to explain now, but in the degenerate case, it's like 1 over square root of the length of the crystal, not 1 over L as one would expect. But it's clear what actually the shorter the crystal, the broader the spectrum. It's always like this in nonlinear optics, but it also has this square root. And then the uncertainty in the positions difference is given by the total angular width. It's also clear. It's like the like in diffractive optics, the broader your divergence, the more certain is your position. And here it's the relative position. And the same with the angle, it's 1 over square root of L. And I just want to show that I think the broadest case of the spectrum, and this is, of course, I like to cite my papers, sorry, but I also cite others' papers. So we recently discovered that if you generate spontaneous parametric down conversion with a very thin layer, and this layer was, for instance, in this paper, it was sub-wavelength, it was 300 nanometers. Then the spectrum, what we observed was about 150 terahertz, but this is only because of our because of our detection restrictions. Our detectors didn't see here, and something cut, a filter cut here, but we saw already 150 terahertz, and this corresponds to very short correlation times and distances. Yeah, so actually I finished my first part. I just wanted to say that they can be sub-wavelength and sub-cycle, these correlation times and distances. And this was the end of my first part. Second part is only, as you see, about 1/3 of the talk. So I think you can use this time for questions. Yeah.
Thanks, Maria. So I think what we'll do now is we'll plan to we'll take the next 15 minutes as time for questions. And for a break, and we will continue with the final part, with the third part at what is here 5:40, and what is in your time probably 4:40.
Yeah,
right?
yeah.
And this will give us time for questions and for a bit of discussion, and also for rest between the parts. The second part will probably go into more recent advances and also what we are curious to do in the lab.
Second part will be about, sorry, the second part will be about the bright case. Yeah, the first part was already about the recent things and what we can do with the lab, but the second part will be about bright.
Yeah, no, I mean from our side, if we want to think about strong interactions of quantum light, we are mostly able to use the brighter sources. So that's what we may have more questions from my students here as well. But I think we'll open the floor for questions, and I already said when we will continue for the next part of the talk. So anyone who is interested in taking a longer break is also welcome to do that. And if we have questions from anyone, this is a great time to come with questions. So we see the audience have questions to ask us. I want to ask something that is related to. Let me start and see if people join in with questions, because there is one aspect that I think is interesting from the point of view of a source of light. Let's say a light emission from that is not necessarily entangled with another photon, but can often be entangled with something that is still inside the material.
Yeah.
I can think about scenarios like this in fluorescence. But actually the most common analog of that is happening for us with electron emission. We're doing photon emission all the time. The electron that's flying out is a single electron. We try to understand the coherence of this single electron. This is a topic of actually quite a lot of debate in the community of photo-emitted electrons. We see also in electron microscopes, but not only. And one of the questions that people don't know the answer all the way through is what part of the single electron is coherent and what part of it is actually not necessarily coherent. And I think it relates to its entanglement to what is still inside a solid. So is it possible to describe it with the same kind of formalism? Say it's entangled to another electron in the solid?
Well, I'm not sure about electrons, but I'm sure that there are entangled states of photons with excitations in the solid. And namely, if you consider the case where the idler photon becomes more and more shifted to infrared, then it becomes a phonon at some point. It becomes, sorry, a polariton. As its frequency approaches the lattice of vibration frequencies, then it is no more a photon, but it has joint mechanical and electromagnetic energy, and unfortunately it doesn't really leave the material. It stays in the material, but if you somehow can record this, detect it, then I'm sure that you can measure some kind of correlations.
So measure whatever is left inside the material.
Whatever is left inside, and by the way, it gives me some idea right now, because if your material is very thin, maybe it still exits the material.
Yeah, if it comes as another kind of excitation, polariton, blip of current, anything of that type.
Yeah, plasmon as well. Well, I think there are even works where they look at the correlations between photons and plasmons, but I'm not sure I have the papers, but I think I've seen works. Yeah.
Going back to the paper you mentioned with the time there is with the time measurement, with the time correlation. So there the actual process is also based on pulses. But the SPDC is driven by pulses. When generally do you choose to work at ultrafast pulses for SPDC versus CW sources that we see a lot in quantum optics as well?
Yeah, well, for pulses, if the pulse is very short, the problem will be that it will not generate photons coherently through the whole sample, because there will be a walk-off, temporal walk-off. The pump pulse will travel away from the signal and idler pulses. So this I would take into account. Then what else? Well, CW pumping produces much more tight correlations. Here, for instance, if you look at this frequency entanglement of frequency two-photon amplitude, the conditional width is given by the spectral width of the pump, roughly. Because it's just, you can imagine, I write omega signal plus omega idler equals omega pump. the reason why it should be aligned is that omega pump has some uncertainty, and the uncertainty of the omega pump is its inverse pulse duration, right? So it's, if it is a pulse, then this is broad. And so for CW SPDC, this will be so narrow that it's difficult to measure, but why should one care? Yeah.
That goes along with the fact that the unconditional uncertainty in time should be
exactly.
Right?
Yeah.
Oh.
Yeah. Yeah.
Okay, thank you, Prof. Following the lecture, the program is. Okay, the light usually helps my eyes, so
Sorry?
Okay, thank you, Prof.
I think he's just on the phone or something.
I don't know, Christopher, you have some echo on your side.
Okay.
Let me see if he's fixing the microphone. Otherwise, I'll mute you, but unmute yourself and see if you can speak with no echo. If people.
So actually, I have a question. Meanwhile, in the same experiment, so we have this weird situation where you use up conversion to increase the resolution, but then you'd still expect. I mean, let's say you have some long pulse, and then you generate a short pulse out of it using this up conversion. Right? If I understand, that's what's happening.
It's up conversion of single photons. So okay. you can convert a single photon to a higher frequency by pumping strong enough. So this up conversion is not shown here.
How does it help increase the sampling resolution?
Because you will look for correlations between up converted photons. Up conversion can be considered as just conversion to a different range, to a different frequency range, but it can be nearly 100% efficient. So nearly every photon will be up converted.
Yeah, no, so, why does this add resolution? Like, why couldn't we just do this in the normal photons before up conversion?
Well, you cannot do it with the normal. If you just detect the photons, you will have resolution given by the jitter of the detector, and that will be 100 picoseconds, right? But when you do up conversion, it's like placing slits in front of the detector. A detector in the spatial case, yeah? For instance, let's go to this spatial experiment. Yeah. Oh, yeah. Oh, I don't know why. Why?
That's the one by Boyd.
Yeah. If you, yeah, here you see the detectors collected here broad angles, but there was a slit, and the slit was scanned. And in femtosecond pulse regime, they scanned in time the pulses, the femtosecond pulses that worked like a filter for transmitting the photon. They up-converted the photons and therefore made them detectable.
Okay, so part of the up-conversion is also like kind of like scanning with your...
Yes, I believe so, yeah.
Okay.
Yeah. It's not my experiment. I don't really know all details, but I can guess that it was.
That's limiting you in time in a similar way that limits the aperture limits you in space. That's
yes.
Kind of
Yeah.
What do you think is today the simplest way to make a measurement that shows entanglement? What is, in retrospect, like what would be the best way to show? Let's say we want to develop a student experiment to demonstrate it. What will be the easiest way to do that?
Well, first of all, you want frequency entanglement or spatial entanglement?
Well, I would, from my side, frequency entanglement.
Frequency entanglement,
but for a student lab, it could be the simple, whichever one is simplest.
Yeah, I think the simplest way is to use CW. Well, you will never measure it because you will never resolve the CW frequency with a student experiment, right? But you will at least estimate it. So what I would do, I would pump with CW and then send to a fiber and measure, well, how to resolve this width. So I would just measure in frequency domain first of all.
Don't you just need to prove entanglement? If you want to measure exactly how much entanglement we have, you'd have to resolve it. But if you just want to prove entanglement, you can just put an upper bound on it. So as long as the uncorrelated is larger than the unconditional is larger than conditional.
Exactly. Yeah. So I would just do this measurement, and I would do it with fibers. So I would send signal and diagonal photons through the fiber, and then look at the time distribution of the coincident clicks, so to say, at the distribution of the delay between the two photons. And this way I will infer the spectrum.
Can you do that with CW?
Yeah, of course, because with CW, you know that signal and diagonal photons will be delayed in the fiber differently. And then after the fiber, the time delay between them will be in one-to-one correspondence to the frequency difference.
Yeah, but because it's a CW, you're constantly generating photons. So how do you know that, like, the photon?
But you will look at different time arrival difference. You will
but
use
it's CW, so there's always more photons coming in. Like, how can you tell if it's a photon coming in from a few picoseconds in the future that got delayed, or one that got from getting sped up?
No, look, you first no fiber, for instance. You just put this setup with a coincidence circuit that I showed you. Yeah, two detectors. You can put a beam splitter, so that if it is okay, if you have non-degenerate case, so if you have signal and either different at slightly different frequencies, then you can put a dichroic beam splitter and send signals to one detector, others to another detector. Yeah, no fiber. So the detectors will click simultaneously much more often at some time delay than need to. Maybe I will now. Okay, I will go to my. Screen sharing has stopped, so I'll share my all my slides. Oh no,
if you want to take a quick break before we continue, we may want to continue this question after. If you want a quick break, we have like 2 minutes before we go back to the third part.
That's okay. I just want to answer the question.
Depends on whether you want a quick question, then I'll ask Michael to wait to the end or to after. Otherwise, it's also okay
probably, now. Yeah. This is just some slide that I had. So this is the time difference between the arrivals of photons at two detectors, right? And there is a peak always here. This peak is not very pronounced, but usually a very high peak, telling you that most of the times the two detectors get photons with zero delay. And this level is called level of accidental coincidences. So you will always have pronounced peak. But then if you add a fiber, this peak will spread because this peak is contributed with photons at different frequencies. But after you add the fiber, the photons of different frequencies will arrive at different times, and this will tell you what the spectrum is. You can calibrate it to infer the spectrum. Of course, you can put two monochromators and scan the slits, but I think it's not a good for students experiment.
So that will be the best.
Yeah. So that was the answer.
I think that. I have another question that relates to this, but I'll keep it to later. Because we want to go back to the talk, and I'll bring it up either during the talk or after. That is related to the femtosecond driven or picosecond driven scale. But let's go back to the slides.
Yeah. So I will.
Minutes to.
I will now pass to the.
Yes.
Let me just check. I don't like. Okay, so what about bright strong pumping of parametric down conversion? If you pump it stronger. You have many pump photons, you have many signal photons, many idler photons. They overlap, but there are still some quantum features of this radiation. And here I wrote again the mean number of photons and again this hyperbolic sign squared. And you see when you have chi2 high or the pump strong or all of them, then you have this exponential behavior, because now the Sinch function is not anymore a linear function. It's an exponential function, and if you increase the pump power, you will have signal number of photons increasing exponentially. And the typical numbers are 10 to the 13, and this is the picture I keep showing. And this is called bright squeezed vacuum for the reasons that I will explain in a minute. So it has important features. First of all, it has high brightness, and so it interacts strongly with matter and with light. Then it has very strong intensity fluctuations, and I will show you in a minute that this is very good for harmonic generation, for instance, and for other multi-photon effects. And finally, it has quantum features, which is photon number correlations and quadrature squeezing. So what happens here? I want to show you, just to impress you once again, this is a typical experiment. A person holds a paper screen and you see one of these beams as we tune the crystal. The beam changes the color because we change the phase matching by tuning the crystal, and the color of the signal photons changes, but it still pairs. The idler photons are at the infrared frequencies, and so you don't see them. But still, this source generates photons in, although large numbers, but always the same numbers. So n photons in beam A and n photons in beam B. And this is a quantum effect. Suppose that we can separate signal and idler by some kind of beam splitter that unambiguously splits signal and idler, for instance, by polarization or by color or by angle. And then if we can register number of photons in the signal channel, number of photons in the idler channel, and look at the variance of their difference, and then normalize it by their mean, normalize for the reason I will show you. So if this value is smaller than 1, it is non-classical feature, because the short noise level corresponds, and I will show you now what is short noise level. For this noise reduction factor, this is called noise reduction factor, the variance of the difference of the photon number normalized to the mean. So the short noise level is 1, and if you're below, this is non-classical, this is quantum. So why the short noise level is 1? Because imagine a perfect beam splitter and a classical beam. It can be a coherent beam, it can also be thermal beam. But then if you balance the beam splitter so that it exactly reflects and transmits equal numbers of photons, N1 and N2 are equal, you will always have variance of the difference, non-zero. Because you can imagine that just the light consists of photons, yeah, we know this, and sometimes these photons go here and sometimes they go here. This is probably, again, hand-waving argument, but if you do the calculation exactly, I can hint at this way of thinking. Imagine this is a coherent light. Then after the beam splitter, this beam and this beam are independent. Then the variance of the difference is the sum of the variance from the probability theory, and some of the sum of the variances, and the variance of the number of photons is equal to the mean for coherent light. So we get this formula. So for classical light, the variance of the difference is equal to the mean sum. But for bright squeezed vacuum, for bright twin beams, this is not the case. Please ignore the many points here. I just show you a picture where this is the short noise level, so the variance of the difference equal to the sum, and we got about 8 dB twin beam squeezing with numbers per mode, not very large, per pulse, about millions of photons. Okay, now about quadrature squeezing. So how quadrature squeezing appears? It appears when photon pairs are emitted into a single mode. This is important. So they should be emitted collinearly with the pump at exactly half of the frequency, so in the degenerate mode. Then the Hamiltonian has this form, as I showed before, it's just A dagger squared. And then Bogoliubov transformation in this case takes the form, simplified form, so the output photon annihilation operator is just related to the input photon annihilation operator and photon creation operator. And then it's convenient to pass the quadratures. I guess I have only 15 minutes left, right? Do.
We can have we can go a little bit over time.
Okay, but I think I will fit. I don't want to run through this because this is basically
yes, I think it's better that we will even continue till 6:15 and we'll continue with discussions along the way.
Okay, okay.
This is not this doesn't scare us, especially that many of us want to learn this and discuss it with you. So don't be
I just need to know what is unclear. From the absence of questions, I can infer that everything was unclear. So let me.
I think that part of the audience here is interested in, is already familiar with the basics of quantum optics and is mostly interested with this part of the talk. And part were interested in the basics and then came for the first part. Maybe we're too shy to ask questions about this. That's okay.
Okay, it's recorded anyway.
Yes.
So it's convenient to pass to quadratures. And here, be careful. They are also called position and momentum. Q is also called position and P is also called momentum. But this is not position and momentum of a photon. It's position and momentum, generalized position and momentum of a light mode, of a radiation mode. Because a radiation mode in quantum mechanics is treated like a quantum oscillator, harmonic oscillator. Yeah, do not confuse. And so the quadrature, the position quadrature, is just a Hermitian part of the photon annihilation operator. So it's A plus A dagger over 2. Well, this is normalization is can be different sometimes, and the momentum is the anti-Hermitian part. And then if we pass to quadratures, these equations become very, very simple equations. They tell us that the position quadrature is just exponentially amplified if G is positive and real. And the momentum quadrature is just exponentially de-amplified. And here I continue this kind of reasoning. It is convenient to consider the so-called phase space, or the space of quadratures. And for people who are not familiar with this representation, I can say that the position quadrature, Q quadrature, or real part of the photon annihilation operator, is similar to the real part of the electric field. You know, electric field is real. We introduce complex electric field just to simplify our life. We introduce this analytic signal. But the quadrature Q is just the quantum analog of the real part of the complex electric field, and the P quadrature is the analog of the imaginary part of the electric field. And now, what is vacuum? In classical electromagnetism, vacuum is just a point here. But for quantum vacuum, it has uncertainty. So the vacuum is a state, and saying a state, I'm trying to show you the probability distribution of these quadratures for a state of light. And in fact, what I'm drawing is the Wigner function. I forgot to put this name, but because it is recorded, you will remember that this is the Wigner function. So this is a quasi-probability, the attempt to attribute joint probability to position and momentum, which is of course a very poor attempt because position and momentum do not commute. They don't like to have a joint probability. Therefore, this Wigner function sometimes can be negative for some states. But for the vacuum, it's a Gaussian function with a width, the same, well, the width in this direction, and this width gives us variances for the vacuum. Positional momentum, and it's 1/2. I think it's 1/4. I made a mistake. It's 1/4 here. Very well. Okay. So if I apply this evolution that position and momentum evolve according to these equations, that gives me hyperbolas. So note that at any time moment, initially, for instance, position and momentum were for this vacuum state, then they start to evolve, but according to this equation, they evolve along hyperbolas because the product of QP is the same as product of Q naught, P naught. And don't bother about this being operators and not real, not C values like in classical physics, because in Heisenberg approach, and here I'm using again Heisenberg approach, it's very similar to classical approach. And in fact, this phenomenon can happen in classical optics. You can see squeezing of classical light. So if I imagine that every point here evolves along the hyperbolas, here the hyperbola, there will be a hyperbola close to the center, there will be a hyperbola here as well. And then if I just evolve each point, I will go to this distribution, and this is already squeezed vacuum. That's why it is called squeezed vacuum. This is a state that has 0 mean values of quadrature, so it has no displacement, like for instance, a coherent state would be, but it has uncertainty in one quadrature smaller than the uncertainty in the other quadrature. This quadrature will be called squeezed, and this quadrature will be called anti-squeezed. Bright squeezed vacuum, when I say bright squeezed vacuum, I just mean that the mean number of photons is large. And this, of course, corresponds to very, very high squeezing, because you see, squeezing is given by this G, and the number of photons is given by the same G. So when G is large, then the number of photons is sig square of G, and it's very large. And this is what happens in our experiments. But the problem is how to measure this squeezing. For photon number correlations I showed you, maybe I should have dwelled more on how to measure photon number correlations, but you can guess. I just put one detector and measure one large group of photons, put another detector, measure the other large group of photons, and I just have to find the variance of their difference. But this is easy. The quadrature squeezing, to measure quadrature squeezing is extremely difficult because although this Wigner function is very stretched, the state here is has a lot of modes. The state that you produce by pumping such a crystal, even by a very, very nice single mode pump, there will be lots of frequencies at the output and lots of angles at the output. And then you need, to measure squeezing, the standard procedure is homogeneous detection. There should be the state under test is sent to the input of a beam splitter. To the other input, you send a coherent beam, which is called the local oscillator, and then 2 detectors at the output. The beam splitter should be 50-50, so each detector should see half of the input state and half of the local oscillator, and then the outputs of the detectors should be subtracted. The difference photocurrent, or the photocurrent difference of the photocurrents of the 2 detectors turns out to be proportional to the arbitrary quadrature. So it's Q cosine phi plus P sine phi, where phi is the phase set by the local oscillator. And for instance, if phi is 0, you measure Q quadrature. When phi is pi over 2, you measure the P quadrature. But the problem here is that the local oscillator should have exactly the same properties, the same spectral spatial properties as the state you test. And if the state is multimode, it's very difficult to prepare such a local oscillator, not to say that even that it has to be broadband. It has to have the same structure. And it's in practice very, very difficult. But fortunately, my colleagues from Bar-Ilan University, Michael Rosenbrook is probably here, and Avi Kler, designed a very clever way to measure this squeezing using an amplifier, parametric amplifier, another parametric amplifier. instead of this local oscillator. So how does it work? This is my interpretation. I'm actually shy because Michael probably is listening. Maybe I'm saying something wrong, but this is the idea. If there is a parametric amplifier and at the input there is a state psi, which has certain quadratures and quadrature variances and so on, Q and P, and then here I just measure the number of photons. And the operation of this amplifier is governed by the same Bogoliubov transformations that I wrote before. So the output photon annihilation operator is a cosh of the gain times the input photon annihilation operator, and then there is sinh of the gain times the A dagger. This is exactly what I wrote before. But then if I construct A prime dagger A prime, so the photon number, and then do the averaging over the input state, I will get this result that the photon number, mean photon number at the output, is related to the mean, to the moments, second moments of Q quadrature and P quadrature at the input. And the coefficients with these moments are e to the exponential of the 2g and the exponential of the minus 2g. And there is also 1/2. But the values here can be, this value can be very large. Imagine if G, the amplification coefficient or the gain coefficient of the second amplifier, is so large that no matter what the variance Q, this, of the variance P, this term is very small. And besides, the numbers of photons that we measure here, in any case, are larger than this 1/2. And then we can neglect this part, and we get that the number of photons that we measure at the output tells us about the second moment of the quadrature. And if also we know that the mean value of the quadrature is 0, then this is the variance of the quadrature. This is the uncertainty of the quadrature. And then we can do it for homodyne detection of bright squeezed vacuum. And here I show our measurement that we did recently, where the, well, of course, in Bar-Ilan they also measured some squeezing, but I think we measured more squeezing. So I will show our measurement. This is the setup, just symbolical interpretation of our setup. This is the crystal that generated squeezed vacuum, and then we imaged it on the crystal that was amplifying this squeezed vacuum. And we looked in the far field at the intensity, and the gain was 2.1, which means that we generated about 16 photons per mode. This is not much, but we had a lot of modes, and so the number of photons here was large, also with amplification. This was rather bright squeezed vacuum. I say it's bright when the number of photons is much larger than 1, and this was the case. So this was the squeezing, the typical squeezing diagram, quadrature variance versus the phase. It's seconds, but it was scanning the phase, and sometimes we had a squeezing here. This is the shot noise, and this is the result. So we got about 4 dB squeezing and 15 dB anti-squeezing.
Can you actually say something about
the
fact that I think what's something about this measurement scheme that's different from what you showed in the first part of the talk is that you're not limited to single photon to very sensitive detectors, right?
Here, of course, yeah, here, sure. In all this second part of the talk, maybe I should have spoken about our detectors. What we use is, well, in this experiment, it was just a camera, a CCD camera, and not a very expensive one. It was a beam profiler, actually. But our best detectors are so-called charge integrating detectors. It's a pin diode kind of detectors that used in particle physics. where you have a particle of very high energy, it releases some number of electrons, and you have to integrate this number, or to count this number of electrons, which can be about thousands. So for us, we measure the number of electrons released by a single pulse, and this number in our experiment varies from about 1,000 to about 1,000,000. And the accuracy of this measurement is about 200.
So you can tell the number of photons plus minus 200.
200, yeah, because and this is very important, and I didn't even write it explicitly, and I think this could undermine a lot of activities. The quantum efficiencies, if you want to measure squeezing, the quantum efficiency should be high, but in this experiment, unfortunately, this restriction is released because in this method, when you amplify what you measure, you don't have to care about quantum efficiency. In fact, our camera had about 50% quantum efficiency.
Huh. So it's interesting to understand what are the types of quantum optics experiments that do not require a very high quantum efficiency.
First group of experiments, the correlation experiment, did not require high quantum efficiency at all.
So it means anything that's homodining, and
homodining does require, well,
it does.
If you want to measure squeezing, if you want to measure anti-squeezing, then no.
Huh. Okay, so for squeezing it's necessary, but for anti-squeezing it's not. So what is the reason it differs this way?
The reason is because maybe I can, well, to draw it on the iPad I need more time, but as you add loss, the squeezed quadrature, maybe I should show it, yeah, here, for instance. If you compare it with the vacuum is a circle like this, what I'm showing, yeah? And then if you add loss, the squeezed quadrature will tend to this short noise value very quickly. Like if you add 80% loss, then it will be only 20% different from the short noise. So it will be close to the short noise. The anti-squeezed quadrature, if you add 80% loss, it will reduce 5 times, right? It will just shrink 5 times, and it will be still larger than this circle.
So the limited quantum efficiency is similar to having a beam splitter that is adding losses, and that is like convolving with a Gaussian of a certain size.
As well, yes,
right?
Yes, that's right.
And that's why it limits the narrow scenario more than it limits the wide one.
Yeah.
That's great.
Actually, very good explanation about convolving. I didn't think of it. Okay. Oh no, I wanted to. Yeah, I finished the description of this experiment. So we saw some squeezing despite the low quantum efficiency. But for me, it's very important because we didn't care about the mode structure. There were many modes, but this idea of our colleagues is very cool because you see. Okay, effects based on anti-squeezing. We also observed a couple of effects based on anti-squeezing, and I want in the end to mention these effects. I wouldn't say that they are non-classical, but they are still very interesting, and they can be observed for bright light. So the point is that this figure rotates with optical frequency because the phase of squeezed vacuum is this phase, the tilt of this distribution. So it rotates with optical frequency. And then if you plot the field as a function of time, then sometimes the field has very strong fluctuations. The variance is very large and sometimes very small. This is squeezing and this is anti-squeezing, right? And so sometimes it's below the short noise, which is this circle. And very strong field amplitude fluctuations mean intensity fluctuations. And in this connection, it's worth speaking of these correlation functions of higher order. So previously I introduced G2, this is Jn, just normalized nth order correlation function. And it's no wonder because of these intensity fluctuations that this correlation function is just a measure of how strong intensity fluctuates. And it grows with n like 2n minus 1 double factorial. It's not that I'm very excited here, it's just double factorial. It just means the product of all odd numbers up to 2n minus 1. And these fluctuations are stronger than for coherent light and even stronger than for thermal light. And then any effects that depend on this Gn will be enhanced. And the interesting thing is that any multi-photon effects, and I know, Ido, for instance, I know that you had a paper on high harmonic generation, and I do believe that these harmonic generation efficiencies depend on Gn's. And also multi-photon absorption, ionization, polymerization will scale with this Gn. And this means that they will be enhanced from if they are pumped by bright squeezed vacuum. And I'm not showing the experiment here, but we just generated this bright squeezed vacuum and generated from this second harmonic, third harmonic, and fourth harmonic. And you see the enhancement compared to coherent light in the case of fourth harmonic was nearly 100. Well, actually it was smaller. It should be 105, but still efficient.
So what is the highest harmonic ever shown to be created from bright squeeze light? Or vacuum?
I think it's only our experiment. I think before us there was a second harmonic generation from bright squeeze vacuum and absorption and two-photon absorption and two-photon fluorescence was demonstrated, I think. But third and fourth harmonic, we were the first, and the reason we did it, we did it on in a very thin layer of crystal, or actually on the surface of a crystal, where you don't care about phase matching. And I think we even saw fifth harmonic, but we didn't have a detector to detect it.
So you think it went higher than that, but you cannot tell, you cannot see it.
Yeah, well, we are sure that it was there just because of the tendency. So you see the efficiency was higher than coherent light, and the importance is that there are still these fast fluctuations. There are still these femtosecond times. And because of that, well, you cannot create thermal light with such fast fluctuations. Thermal light is usually mimicked by some rotating disks and wiggly fibers. Anyway, I'm coming to my last experiment. We also generated supercontinuum by sending this bright squeezed vacuum at a single mode fiber. It was just a usual fiber. And we suddenly saw that some spectrum is formed around this fiber. We didn't want it. We wanted to filter, but we saw some spectrum. And then obviously this is through four-wave mixing. This spectrum was generated through four-wave mixing. But because four-wave mixing is a very nonlinear process as well, then it's amplification, nonlinear amplification of already fast fluctuations. And then when we looked at the photon number distribution, well, first of all, we looked at the different pulses. And you see that the intensity here fluctuates by 1, 2, 3 orders of magnitude, almost 3 orders of magnitude from pulse to pulse, mainly on the edges of the spectrum. So where this supercontinuum, it's not super, but continuum, some broadening of the spectrum. It's still enhanced. And then we decided to measure photon number distribution in this pulse. And you see that it has a heavy tail. This is log scale here or log scale here. Distribution like this is called Pareto distribution because it follows this Pareto principle, very well known, but it's a power law distribution. Imagine power law distribution decaying so slowly. And if you look at different pulses of this supercontinuum from bright squeezed vacuum, it shows typical extreme events. The mean number of photons per pulse is somewhere here, but you see sometimes pulses exceeding the mean value by 200 times. Well, here is probably 150, yeah, but some other cases there was 200. And it doesn't even converge, this distribution. Its mean value and higher moments diverge, and we can see the so-called coastline paradox. The longer you measure, the larger the mean value you get, for instance. Yeah. So this was just in the very end. I think this is very interesting, and this is an effect that doesn't require any detection efficiency. Yeah, wave behavior. So I came to my conclusion. Yes, I showed you how it appears. I showed you entanglement, and I showed you some effects with bright squeezed vacuum. Thank you. I'm sorry, I was 1 hour and 40 minutes.
Or like 1 hour and 35 and 15 minutes break. That's okay. We really appreciate it. This was really interesting.
Well, I appreciate your attention, first of all, and I was glad to be in Israel, at least virtually.
Yeah, that would be much better, but no, but we still have a chance through Zoom to ask questions and discuss those ideas. And I have a couple, and if people have other questions they want to ask, it's also a good time. I want to first ask something that relates right to the last few slides. That relates again to the emphasis on squeezing. Maybe you can say a few words on this. About the reason we are excited about squeezing. What are the immediate applications or the places we think we would be able to use squeezed light?
Well, I think that squeezed light is most practical way to improve measurements for metrology, because you saw the uncertainty can be very small. So for instance, if you produce a phase squeezed light, you can measure phase very accurately. In interferometry, it is known for years, it was an old proposal of Caves how to improve gravitational wave detection, for instance. A gravitational wave is a gravitational wave detector is an interferometer. And you showed ages ago when you send a squeezed vacuum into the empty port of the interferometer, instead of sending vacuum there, you have enhancement of the phase sensitivity. And this is actually used in LIGO. The problem here, the bottleneck, is that you also have to detect efficiently. But for this bottleneck, Caves also suggested a remedy that is parametric amplification before detection. We are now we did an experiment trying to advertise it, but it seems
so if you use a source of light like you showed at the beginning of your second part of the talk, where we actually see it with our eyes, so it's squeezed and very intense. Is it also a useful squeezed source of light, or is this already?
Well, as I said, this source of light is not so useful as squeezed light, because, well, depends whether you can detect it, as I said, properly. The problem with our source is that it's multi-mode, and while some modes are squeezed, others can be anti-squeezed. This is another thing. And then if you do not select a mode, you detect anti-squeezing spoils all your squeezing because it's much more pronounced. Yeah? And then, but this trick that Avi and Michael invented, this is very powerful too, because it enables not to select a mode and not to detect efficiently, because yeah, you can amplify it before detection. And I think we are going to use it for for increasing the sensitivity of absorption measurement, spectroscopy, even Raman. They have another proposal on Raman with squeezed light here.
So you mean that even if it's a multi-mode source, there are certain applications for which it is useful?
For sure. Imaging, for instance. Well, let me mention imaging. If you have multi-mode, especially multi-mode light, there is a rather famous idea of subshot noise imaging. If you put an object into one beam, and then instead of just looking at the intensity behind this beam, subtract the intensities of the twin beams. So you subtract the intensity after the object from the intensity distribution after the object, you subtract the intensity distribution for its twin. And then it turns out that you can increase the signal to noise ratio. But again, so far experiments were done with the cameras having 95% efficiency. There are CCD cameras with 95% detection efficiency, but obviously this is not very technological, and also efficiency drops even if you have some filter in front of the camera, you know, right? Even the crystal itself. But our idea is to enhance this method by placing another crystal, amplifying the multi-mode radiation, and then you don't care. Then you don't care about losses if you amplify. I think this is a very powerful trick that we're going to make.
That's a method to, despite the detector being a regular one, like a regular Raman or something, and not something with extremely high quantum efficiency, you still benefit from the squeezed nature of light.
Yes.
And then how do you avoid the fact that part of the light is anti-squeezed and part of it is squeezed?
Because as you saw in this experiment with Homogeneous Detection, here, for instance, by the way, this trick that we made, the imaging of one crystal on the other, led to the fact that all field of view was either amplified or de-amplified. So this was the distribution. And if the lens is aligned correctly, actually we didn't have a lens, we had a mirror, and the same crystal doesn't matter. So if it is aligned correctly, then the whole field of view breathes. So maximum, minimum, maximum darkness. But if it is misaligned, then you will have fringes telling you that some modes are amplified and some modes are de-amplified. And if you do it properly, then all modes will be amplified. Then you will measure squeezing for all modes. And Michael and Avi, they measured the same in frequency. They had some dispersive fiber, and so there was amplification, de-amplification depending on the frequency, but still this system works.
That's really interesting. So this is a way to get everything squeezed in a constructive way.
Yes, yes. Or rather to, I might be saying something wrong, not everything squeezed. I think some modes will be still anti-squeezed, but you look at squeezed quadrature for proper modes, so to say.
So in different points in time, we see, that's the, so it basically, you can think about it like it rotates in time, right?
Yeah, it rotates, but it doesn't, it has, rotates in time. You can say that for some modes, the Wigner function is stretched like this. For the other mode, it's stretched orthogonally. There are only two types, odd and even modes in the simplest way.
And for some reason, it's a function of time, because this picture is always for a single frequency, right?
Mm-hmm.
It's for each frequency, it goes differently. So instead of it, you can look at it as a function of time. And as a function of time, it will be, different points in time will be either squeezed this way or that way. It will not mix it.
Now you ask the question I cannot answer. I think this is the carrier frequency, so this is the central frequency. What happens with detuned frequencies, I think that they are pairwise. If you take a frequency omega naught, the central frequency, and then omega naught minus omega, omega naught plus omega, these two pairs of frequencies form a single mode, so to say. And I think that then this picture is a bit misleading, a single frequency. But this is so because, for instance, I said you have to assume degenerate case, a perfectly degenerate case, right? You can also assume non-degenerate case. You can also assume A dagger, B dagger. But then to see this squeezing, you need, or parametric amplification, you need to have both modes simultaneously. So in terms of these two modes, it will behave the same way. I don't know if my explanation is very clear. Probably not.
So both.
Yeah, it's either you have one degenerate frequency or you have two satellite frequencies.
I think I understand, and I will follow up on this separately. But let's see. I know that I have one more question, but I also saw that Lior asked me a question on the chat. Maybe Lior, you want to?
It's a little out of your conversation, so I can wait. I can wait.
Okay. So I have a question that relates to outlook. Do you think that you'll be able to use the squeezed vacuum sources, not just to go to fourth harmonic, but eventually to see high harmonic generation, to 10th of harmonic, or is it far-fetched?
I'm sure we can, because It's very bright. It's just we used a material where typically high harmonics are not observed. We just used a slab of lithium niobate and focused on its surface. So the powers that we have, I can give you numbers. We have about a few hundred milliwatts on the average, but the duty cycle was it was something like 10 to the minus 7. Yeah, so we had 5 kilohertz rep rate and 1 picosecond pulses. So it's what? It's about 10 to the minus 7, and means that the peak field was 10 to the 7 times higher peak power than 300 milliwatts. So it's in that experiment we had a lot really of energy. And I don't know what energy people use for high harmonic generation, but I don't think it's much higher than that.
Oh, once you're working at hundreds of milliwatts at 5 kilohertz repetition rate.
And a picosecond.
Yeah, it's already
100 milliwatts is your average power?
300 milliwatts, the highest average power we got for bright squid vacuum. Maybe 100 milliwatts, but definitely not less. Within the whole bandwidth. And the bandwidth was about at 1600 nanometers. The bandwidth was about 400 nanometers. I cannot say now how many.
Is it possible then to take the output squeeze light and put some dispersion so it gets to a shorter pulse duration? Because you don't really want it at 5 picoseconds. I think that's the only limit. If you can then use that very wide bandwidth to get it to be a pulse of, let's say, a few tens of femtoseconds, then it's definitely going to work out.
Wait a minute, it's not a Fourier transform limited pulse. There are always these two parameters, pulse duration and correlation width. Like the same entanglement that I showed you in time domain for single photons, the same will be valid here. So let me come to this picture again. So this distribution will be also the case for our experiment, only it will not describe single photons, but correlations. So this will be roughly the width of correlations. This will be on femtosecond scale, and this will be the pulse duration on picosecond scale, but you cannot compress this.
You cannot rotate it,
You can compress this thing, by the way, and this is very interesting. I'm sure that you can compress G2. This is the width of correlation function. You can compress it, I'm sure.
You're saying it will not give us a Fourier limited pulse in the end, so we should still expect to get few picoseconds for the pulse duration.
But you don't need the pulse to be short. You need this to be small, I think, because for instance, harmonic generation. This is an almost instantaneous process. For harmonic generation, if you want to observe harmonic generation from, for instance, 2 photons, again, some experiments like this were done in the group of Jan Zilberberg years ago, which now everybody cites. But I think they showed that even 2-photon light can create strong harmonic generation, some frequency generation. And what matters is this, how close these photons, sorry, in time. I'm pointing at frequency button,
Because I'm asking about a pulse duration since I want to get the strongest possible intensity. But you're saying that it's not really just the intensity, it's something else that's supposed to dominate it. And I think you're right. I think we have the intuition that we want high intensity for harmonic generation, but since it's going to be a very non-classical source driver, it's probably not the case. The same reason that enhances the fourth harmonic, it's going to enhance higher harmonics even more.
Exactly. Yeah, I think for harmonic generation, it is not the pulse duration. You need pulse duration, short pulse duration, because you have a coherent pulse for which this distribution is basically a circle.
Are you thinking about doing an experiment like this? Because we can definitely calculate how this...
I was thinking of doing an experiment like this, but I never generated high harmonics. And the other thing is that I spoke to some people who generate high harmonics, and I spoke to quite knowledgeable people, Paul Corkum, for instance. and other people from our Russell division in our institute, and they said that they believe that at high harmonics, this scaling is not the same. So this scaling with GM comes from the fact that the intensity of an nth harmonic scales with the nth power of the intensity of the first harmonic, of the fundamental. Then it is straightforward. So if intensity scales as the input intensity to the power n, then you do averaging and you get this GM. This is just
right.
information. But they say that at high harmonic rates, this scaling changes. And I don't know why, and because they were not especially interested in doing this experiment, I didn't continue further. But I still think that there can be lots of things, because for instance, fourth harmonic is doing this perfectly well.
Yes. It's known that in harmonic you don't have the same efficiency because there is a plateau at many of the harmonics. So that means that we will not expect the same behavior anymore. It's like a non-perturbative range of nonlinear optics. But that doesn't mean that there is not going to be an interesting enhancement happening at very high harmonics.
Exactly.
And that's actually a very interesting challenge, because so far when we did quantum harmonic generation, and if Alexei is here and can unmute, maybe he can refer to this.
Yeah, I'm here.
Yeah, so Alexei is the one that actually did the first work on QED for harmonic generation.
And I read the paper, but I think what I read was theoretical, no?
We assumed that the driver pulse is classical, is coherent, the coherent state, because we didn't think that a squeezed source can actually get high enough number of photons like you have. And then we quantized the emission. But we can definitely apply, the paper does cover the case where the driver can be a squeezed source. It's just in the supplementary, you have the full formalism. We just never tried to apply it to see what happens. Alexei, what do you think about this? About trying to have the driver a fully squeezed vacuum source?
Fully squeezed vacuum source, I think it will be something interesting, at least something unexpected.
Right. It breaks the basics, the most basic thing, because what we had there is we can move the statistics of the coherent state driver by a displacement operation to be a time-dependent change to the Hamiltonian. That's how we got the time-dependent Schrödinger equation. Even that's not going to hold anymore. Even that's going to break, right? So the most basic thing we do in harmonic generation is not going to be legit.
Well, actually, when we started these experiments, someone from my Moscow colleagues said, "Oh, you will have a UV catastrophe." I said, "What's the UV catastrophe?" And he said, "The UV catastrophe is because if you do harmonic generation, even in material, chi nth, the nth order susceptibility, which is required, for the harmonic, scales as a power law with the on the other hand, G nth scales exponentially. So the susceptibilities become smaller and smaller, but they scale as the power law. It's basically the ratio of the field to the atomic field, to the interatomic field. And so then at some point you will have just stronger and stronger harmonics.
But I guess this is still, if we think about the chi of omega, the nonlinear ones, as in a kind of perturbative way. But at large frequencies, I think the susceptibility will drop for other reasons, like the material response is almost zero at high enough frequencies.
That's the point. It decays at at high frequencies. Yeah, that was the solution of the UV catastrophe.
Yeah, exactly. Because you ionize the electron with a single photon, you're already ionizing.
Yes.
Single emitted photon. So I think that we need to calculate this. Alexei, Michael, we have to try to think what happens if we will not be able to go through the time-dependent Schrödinger equation. Let's think what happens instead.
Calculation is okay, but do you think it's possible to do an experiment? Because this source is really very big, because we pump with tie-soft laser, with regenerative amplifier, we pump with 3 watts, 800, this parametric down conversion. And then parametric down conversion, we make it very efficient, but we do it by pumping very strong. And then I thought that harmonic generation, high harmonic generation, you need some gas, some very complicated.
Yeah, we need some space in the lab to put the. I mean, we should discuss with Owen Cohen on what is the most simple way to look at some harmonics. What kind of gas? Because it's probably more likely to build this kind of thing in your lab than to move the entire generation. Right?
Moreover, I can tell you that we have a lab neighbor, a person from our institute who has set up with some gas and a parabolic mirror, and maybe we can join efforts with him. If you come up with an interesting theory, interesting proposal, we can probably do it.
Okay, this is homework for us, Alexei. We want to think.
But I think it's a question whether it's possible to make such large intensities, which is required for high harmonic generation with squeezed vacuum. I mean, it's 10 to the 14 watt on centimeter squared. Yes, the intensity.
I think it's not far-fetched. If you try to put the numbers. You have 100, let's say, milliwatts, maybe 300 milliwatts, with just 5 kilohertz repetition rate. The energy per pulse from that is definitely on the scale that is used for harmonic generation already. That is. I mean, it's not it's not the highest, but it is on the scale. Now, if you focus it effectively in space, then I think it should be on the right order of magnitude. The duration in time is a little bit tricky because it's a factor of almost 100 longer than what's normally used. But the energy per pulse is higher than the lower limit. So I don't think it's going to bring us to hundreds of harmonics, but if it can give us 9, 11, like a number that is beyond perturbative nonlinearity, but is already to the beginning of a plateau, then it's definitely worth doing it. And hopefully it's enhancing it. That's the theory, for the theory to say.
Yeah. The point is that it should be enhanced. It should be enhanced by GN, and I don't have here the. Maybe I can show some graph with how these GN grow with the order, and they grow very, very, very fast. Probably I should it's faster like this. Yeah. This plot, yeah. So this GM with the order. So for instance, if you speak of 10th order, this factor is 10 to the 9 provided by the correlation function.
So if it grows like GN, which is what the theory that we should do must predict, if that theory should describe in harmonic generation, it's really the dynamics of an electron that's ionized and what it's going to do. If the wave function of the electron changes in time in some way that is still going to follow a similar kind of enhancement, in the end, we want to predict a GN enhancement. If that's the case, then yeah, that will be amazing. Right? What is going to be enhanced in that way?
Yeah, I think if there is some theory, it will be more safe.
Definitely.
I have a question actually about this GN. So what do you mean when you say bright squeezed vacuum? I mean, I know it's kind of like a silly question to ask this far in, but do you mean like one that's completely a line at this point, or because I'm missing all kinds of parameters about how squeezed the vacuum is in this G, right?
You mean
like if it's like very slightly squeezed vacuum, then I guess it doesn't
large G or small G? I didn't.
Small G.
Small G, but
this one that goes like the second factorial.
This correlation function?
Yeah.
Well, this correlation function has to do rather with anti-squeezing, as I explained. It's a measure of intensity fluctuations. Even if you take thermal light, or for instance, light that comes from the sun or for heated bodies, G2 will be elevated. G2 will be 2, and Gn as shown here. But what is squeezed?
No, it's more like how. So for coherent light that's not squeezed at all, this ratio doesn't hold, right? Because it's just,
For coherent light, G2 is 1, Gm is 1.
Yeah.
Always.
So what I'm missing here is like what parameter goes smoothly between these distributions?
Okay.
Like how? Because I'm missing like some parameter like how squeezed.
That's a good question. I can tell you, for instance, how you move between coherent and thermal. Probably you can imagine that. Even if you take a usual bad laser, just a usual bad laser, it will be somewhere in between, because it will have excess fluctuation. It will have not only shot noise, but it will have instability in the intensity, classical instability. And this will already increase G2 and Gn. So it will go somewhere in between. Now the difference between a bright squeezed vacuum and thermal light is that thermal light you can imagine as just different coherent states for which amplitude is different. So you can imagine thermal light as a superposition or mixture of course, of coherent states with different phases and different amplitudes. For squeezed vacuum, yeah?
Can you actually write that with, if I want to write the density matrix of thermal light, I would do that as a sum of Fock state basis on the diagonal.
Yes.
Can I do the same with a bunch of coherent states with different phases? So the density matrix of thermal as a sum of coherent states?
Okay, now I have to write something. This is really difficult. I'm not sure. I take into account that they can write some rubbish. Okay.
Let's see. For now, I see a black screen, but not yet the.
Yeah, because I have to make some tricks to.
Like I said, this is connected to what we discussed yesterday, actually. Whether we can write the density matrix of, let's say, thermal state with the basis of Fock. With Fock, we know how to do it. Can we do it also with thermal, with the coherent states? Okay, now we can see.
With the coherent. But I think you can diagonalize your matrix only on a special basis, not in all bases, right?
Yeah, but then, so what is the meaning of writing thermal light as a bunch of different coherent states with different random phases? There is some connection between the two. So how does it connect to our discussion? That's what I'm trying to understand here.
Yeah. Now I think you see my
yes.
pad, yeah? Let me first draw pictures, okay? Because I would prefer to draw the Wigner function Q, P, so a coherent state, something like this, right? A thermal state is something like this. So you can imagine that this is a superposition of different mixture of different coherent states. So how to write the density matrix sum, and then there is this alpha n, right? Alpha n, sum over n. Yeah, so squeezed vacuum. But for these coherent states, the phases are all different and the amplitudes are all different, because this is the amplitude and this is the phase. Now the squeezed vacuum.
So if you write the rho over as a sum or even integral over over coherent states like this, are you with alphas having different phases and also amplitudes? This will give us exactly the thermal state?
Yes, I'm sure it will. Yeah. Now, yeah. So of course, if you want the integral, if you want the integral, yeah, it will be d phi d modulus alpha. Yeah, I'm not a theoretician, so you should have this alpha naught, yeah, alpha naught e to the I phi. And then the same complex conjugated, yeah. So you write something like this. But I want to stress that for squeezed vacuum it will be different. For squeezed vacuum, it has this shape, sorry, Q and P, and then I think that the mixture will be only for states with different amplitude. The phase should be the same, or 0 pi.
Yeah.
Well, how I derive that Gn is 2n minus 1 double factorial is a different way. You just do this Bogoliubov, and then you calculate a dagger to the power n, to the power n, average over there. So you substitute here Bogoliubov, here and here Bogoliubov, you average it over the vacuum state. Yeah,
you get a double factorial from the...
You get this double factorial. There is an old paper where this was derived, paper by Jansky and Yushin. If you want, I can send you a link. But maybe the same intuitively can follow from this model that you just consider coherent states displaced like this with the same phase but with different amplitudes.
Interesting. So I think that part of, maybe it's connected to what Michael asked as well, is if we want to distinguish bright squeezed vacuum from, let's say, the regular squeezed vacuum, is this only through the fact that normal squeezed vacuum is barely 2 photons and bright has many more?
No. Here I want to stress something. Squeezed vacuum is when you, squeezed vacuum is when, for instance, delta Q is much less than delta P, or rather, well, this is not very strict. The strict definition is that delta Q is less or much less than delta Q0, which is for the vacuum. Delta Q naught is for the vacuum. So whenever you have this, you have squeezed vacuum. But this 2-photon light that I described has almost no squeezing, because this happens when the parametric gain that I introduced, the gain for this should be about 1. Enough. 1 is enough, because delta Q, as I wrote, is e to the minus g delta Q0. Yeah, so if G is on the order of 1, this is already squeezing. But the biphotons that I described, biphotons correspond to the case when G is much less than 1, for instance, 10 to the minus 5. If you have G on the order of 1, you will have many accidental coincidences. You will not see this coincidence peak. You will not see 2-photon correlations, really.
Yeah.
And also G2, in this case, G2, as I wrote, will be 2 plus 1 over mean number of photons. So if this is large, the G2 is, well, this is for signal idler case. But for G2 for degenerate case, signal degenerate case, will be 3 plus 1 over n. And 3, if you can notice that this is 2n minus 1 double factorial if n is 2.
Yeah.
This is exactly this case. So all these strong fluctuations effects have to do with this term in G2, and pair correlations have to do with this term in G2.
It's all for G much smaller than 1, and then...
Yeah, it's all for gain much smaller than 1, yeah.
Yes, and that's the case that is... Then, so why then call it bright squeezed vacuum versus the regular?
I call bright squeezed vacuum when G is much larger than 1. G much larger than 1. I call it bright squeezed vacuum because we see the output number scaling with the pump power, yeah, exponentially, and it means that you can really convert considerable amount of the pump into this squeezed vacuum.
Which still means that the number of photons is much bigger, of course. So that's bright comes from that, but also the delta Q is very small.
Yeah, delta Q is also very small. It's extremely small, but then, as I showed, this Wigner function maybe looks like just a line, just stretched because this. But then the problem is that if you impose a little bit of loss, even just dust in the room, then what happens is this convolution, as you said, with the vacuum. And the convolution will immediately spoil the squeezing, so the squeezing will be given not by the initial gain, but it will be given by the loss.
Yeah, but that's still correct for G about on the order of 1 and even smaller than 1. Why is it more sensitive when G is much larger than 1?
Wait a minute, G much larger than 1 here.
You're saying it's more sensitive
G
for
much
G large.
smaller than 1, you get no squeezing. With G much smaller than 1 here, you have 1. It's
Yeah, you have nothing.
So most of squeezing experiments, not our experiments, but normal squeezing experiments where you have crystal in a cavity, the cavity selects a single mode. This is CW pumping usually, CW pumping. Typical values are G about 1 to 2. Then the mean photon number is about 10, yeah, something like 10, 20. Yeah. But the squeezing is already very high. E to the, so delta Q squared will be e to the minus 2g. So it will be about 10-15 dB. Squeezing is measured in dB. And then it will be approximately the same as the restriction imposed by the loss, because here the squeezing is almost infinite, but the loss immediately, your convolution argument, turns it into like 10 dB squeezing. If the loss is maybe 5%, it's about 10 dB squeezing, if I remember correctly. I remember that a loss of 3% and infinite squeezing gives you 15 dB squeezing after the loss.
So is it more, but is it less sensitive to the noise of a single speck of dust or convolution with vacuum when it's in the mode like this?
Well, it's sensitive to the loss. I'm not talking about noise. Noise is another thing. But if you have, for instance, here you have 100 dB squeezing, then you have 3% loss. You have 15 dB squeezing. Why is it more sensitive? Because it's the convolution. Because if you have initially your state like this, you do convolution with the vacuum, and it doesn't spoil you much your squeezing.
So it spoils less than
yeah, because it's like doing convolution for a very narrow function and a very broad function. So if the function is very narrow, then after the convolution, the width is given by this function. But if the function is broad, then after the convolution, it will be almost the same.
Yes, that's true. I see it's more sensitive, but not. It's still the same convolution, basically. Okay, I understand the. So, but bright is coming with the number of photons and with the large size of G. Up to a different G, squeezed vacuum and bright squeezed vacuum would be the same creatures.
I just use the word bright for stressing that the number is very large.
It's much larger.
Yeah, it's much larger. In principle, in my terminology, the squeezed vacuum that is obtained, for instance, in the Hamburg group of Roman Schnabel, he's a champion, I think, and world champion in squeezing. They have 15 dB. Then the number of photons is about 15, which is already rather bright. But of course, with this state, you cannot do harmonic generation.
But their advantage on what you showed is that they have less loss, but not that they have more G. They just have less. The loss is lower. Is this right?
For them, yeah. For them, the loss is lower. Yeah. Well, yeah. The loss is lower. The original squeezing is worse than ours. But again, if you want to measure squeezing very accurately, you don't want very high G, because then you will have high anti-squeezing, and anti-squeezing will contaminate, if you want, contaminate your squeezing, because if you do homodyne detection, or even if you do this parametric homodyne, that what we did, there is still some problem introduced by anti-squeezed modes, I believe.
Yeah. But it's not the anti-squeezing of this same frequency, it's anti-squeezing of neighboring frequencies?
Well, when I say different modes, again, if you have a central frequency omega naught, then there is a sideband, for instance, omega naught minus omega, omega naught plus omega, but there are also other sidebands. So when I mean a mode, I mean this mode together with this mode, right? And this is another mode, this is another mode. So modes include symmetrical frequencies.
Yeah.
Or you can do, you can speak of broadband modes in terms of Schmidt decomposition of the spectrum, but this is, I think, it's too complicated.
Nice, I see. So that might what mixes different modes and makes squeezing problematic. It's not in the same. It's not at the same mode. It's always the neighboring modes doing that.
Yeah. And as I said, half of modes are squeezed like this, and half of modes are squeezed like this. It means that when you measure, for instance, Q quadrature, you want to measure squeezed mode, this one, but the other one will always interfere.
Yeah. And that's for us to understand with another discussion for why is it always coming together, strong squeezing and under-squeezing. But I'll not go into it, because otherwise we'll...
Why they come together? Because you know, delta Q times delta P is larger than H bar now, or in my notation is 1 over 4, I think.
Actually, I see that Nick wrote something that is interesting into our discussion on HAG. And if we're looking for the impact of higher order very strong squeezing on higher order nonlinear effects, maybe instead of looking at higher order harmonics, we can look at multi-photon ionization, what is called above threshold ionization, ATI.
As well,
Could also benefit from that, and that may actually happen at much lower intensities. If we use the right piece of metal and we have an electron spectrometer, we shine a light on the tip, we look at the electron energy. Those are simpler experiments considered.
Perfect. Maybe we can ask Peter to help, because
yes, actually that's an interesting. Do you know if anyone ever tried that?
No, nobody definitely tried that. I know that we were first with bright squeeze vacuum going higher than second order. The previous work was by Claude Fabre. I think they did such experiments with absorption of fluorescence. I think there was one fluorescence, I think, 2-photon fluorescence they used.
The theory for this is easier. We don't need to have the quantized emitter field, because we only have the electron being modulated by the field. So there is a simpler form of strong field QED for us to apply. In this case, we solve for the dynamics of that electron under the field, external field, and we can make predictions. We need to ask Peter if their group ever measured the above threshold ionization.
Yeah,
we consider a simpler experiment. Only a tip can do it. Although many of the experiments there are also with gases. So we need to ask him what he thinks is easiest.
Actually, maybe who could consider ionization was, you know, Peter Lambropoulos? He's a Peter Lambropoulos, I think Peter.
I don't know him for
He's one of the pioneers of all this. You see, here you can probably, no, you don't see my previous screen. I cited one of his papers, and I will now stop sharing this screen and share another screen, which is.
So he was also doing.
Yeah, you see here this paper. It's 66, and at 66, people didn't speak about squeezed vacuum, but they spoke about the role of GM in multi-photon processes. And I know, by the way, that there was a paper, which I do not cite here, about 11-photon ionization in thermal light. But in thermal light, but thermal light provides less efficiency. This is one thing. And the other thing is that thermal light is never doesn't have these fast intensity fluctuations. It's because to make thermal light, people usually just modulate coherent light. But yeah, Peter Lambropoulos was calculating something for squeezed vacuum, and some I think ionization, but I think it's always 2-photon or 3-photon. It was theory. And recent papers as well. He was very interested in our experiments. And he wrote some theory about, but I think he was mainly interested in the resonances. So if the ionization is, or absorption happening through resonance.
1966, amazing.
Yeah, but yeah, everything is a bit reinvented. And
So
at that time, yeah.
We will discuss. We'll think about this as well, about threshold ionization here. I think is definitely valuable to do as well.
Okay.
This is really interesting. Okay, we are. I have one more question, but I don't know if we're still up to it, because this is really interesting. So if
well, the number of people is reducing and reducing. I think
this is likely,
as long as I'm here.
We now have mostly people who are the most excited about it or connected to the group in some way. We still have some group members, and we have friends from MIT still connected. You can say hi. So I think it's those are people that are most connected to what we are discussing, because it can also lead to future ideas and things we can do. Do I want to ask one more question or leave it to another discussion? Let me ask you a brief one, just because we're already at it, but stop me if you're desired. Because the discussion just led to a lot of other things that I was thinking along the way. When we're thinking about the femtosecond processes of, let's say, SPDC, right? And we are looking into the emitted light. What if we had this process done in a form of a pump probe, where the probe will be the one producing the SPDC, like you do now, but we bring a pump before. That pump is intended to do some kind of coherent control on the material. So we modulate it, change the state of atoms of the solid in a way that takes some time to relax back to ground state. It didn't relax yet. And now we have an out of equilibrium material that is coherently controlled, excited, something that is doing the SPDC. How is the emitted light going to change because of that?
I can imagine that what you can change is linear properties of the material, and you can change nonlinear properties of the material. Or you can, of course, you can excite, if we speak about this hybrid pair, photon and some lattice excitation and some phonon and so on. So you can probably excite and then scatter by this. You can excite, for instance, a plasmon or an
So.
But then to me it sounds a bit not so interesting, because it loses the quantumness, because the correlations are related to the fact that there is no intermediate. It's not stimulated. Both photons are emitted at the same time. But also you could probably change the nonlinear susceptibility, but I'm not sure it's so easy to
So is it possible that we will enhance quantum properties of light because of that? We'll get something new?
I think it's very interesting. It could be, and maybe it's especially doable on the nanoscale, because I don't think you can change very much nonlinear properties of a bulk material. But if you have some surface, meta surface, today my brains are really around meta surfaces.
So that's another topic that are you familiar with any literature that has ever tried that?
No. But I'm familiar. I know that very, very popular now is nonlinear optics at a nanoscale, and also people speak of quantum optics at a nanoscale. And I tried to show our papers on the subject, but I think it's just starting. And when everything is so small, you can really change the properties, hopefully, with beams. Yeah.
So that connects well with what is now the most recent advance in the field.
Yeah, but for instance, what I can think of, periodic polling, when you change the nonlinearity periodically, and then you satisfy phase matching. So I think, actually, it was my dream when I was a student, but then it was not possible. And recently I heard that people start speaking about this in time. So if you modulate in time the nonlinear susceptibility, then you can satisfy the frequency. So you can modify the energy conservation, or you can see obviously non-conservation of energy, because like the periodic polling adds the K vector to the phase matching, then the periodic changing of the nonlinearity in time will add energy to the phase matching. I think this is very, very exciting.
I'm curious, what will be the way to model that, actually? How do we even model this is like coherent control experiment on SPDC. That's what it is supposed to be. Michael, that's what we discussed like a week ago when I told you I wanted to think about it. And the fact that Maria is not pointing us to a paper that did it already is already a good sign.
I don't think it has been done. Modification of nonlinear properties. I know that, for instance, there are works where they take fibers which have no Chi2 and induce Chi2 by just applying DC field, just static field, pulling the fiber. This is done in Toronto group. I don't remember the names, but I think they are doing this in Toronto. But this is not exactly what you're talking about.
Okay, so we'll think about that as well. Part for the SPDC about threshold ionization. There are some interesting things for us to consider theoretically first, and then try to brainstorm with you later.
Okay.
There are many things here that are beyond what we can even do in the next 2 or 3 months, but this is okay. That's the purpose. We can think about things long term. Michael here is starting his master this semester and is going forward to going to this field. So I think we'll have more opportunities to jump into this in AJG and also in other ideas.
Well, great. I will be happy to continue brainstorming, collaboration, whatever. If you want to have someone learn the experimental technique, I definitely need, at the moment, I'm even looking for a student to continue. And we could even start this experiment. For me, it doesn't matter much what exactly to do, because all this direction with bright squeezed vacuum is now in my group. It lacks people because I move more people on nano scale.
Yeah, to do things on a... Actually, this talk is a good opportunity to get it more well known around Israel, or especially that it will go on YouTube in the Technion Quantum Center channel. So, Lior, do you want to finish with? I know you waited patiently for, and I'm not sure what's the context of the question exactly, but
Is it to me or to Ido?
It's to you, Maria. Okay. Maybe if you can answer. It's a very naive question. I'm not in the field at all, but I wondered, and I now wonder again: is there any problem or challenge to the constancy of the speed of light if you create some 2 photons in some place at some moment, and you measure a spread at some other defined place, spread in time, does it challenge the speed of light?
I don't think it challenges. Actually, it's very high level for me. I am a humble experimentalist. For me, the speed of light is constant. All I can say is that maybe you can measure it, because some people consider these entangled photons as a way to measure time intervals, to measure, how it's called. I talked for too long. Clock synchronization. I think there were papers on proposals on how to do clock synchronization, and this reminds me of speed of light, right? And whether it's constant and so on.
There is an interest. It sounds almost like very out of the convention physics question of like challenging something that everyone already accepts. But there is one place in physics where this is very inside the mainstream, in asking whether we actually need to define a speed of light as a constant, or can you think about it as a concept that only relates to a closed circle effect? Like There is a discussion on that that was also studied in significant papers. And I sent a link in the chat. This is a very popular piece of physics that also relates to relevant papers. But it's a very good discussion. I recommend it to everyone here, by the way, because there is no way to prove that the speed of light is constant in a one-way experiment, only in a closed loop experiment. And we actually do not need to have a fixed speed of light. That's what he's arguing there and explaining why. I do not know any experiment in quantum physics that will challenge that, but the discussion there is all classical.
I don't know either. Yeah.
So if you're curious about this, I would recommend looking into this video, which is also bringing up a similar question. I don't know if quantum physics can change that, let's call it standard understanding, but it's definitely an interesting question to think about it in this context.
I don't know. I think to deal with speed of light, you need at least to make these photons propagate somewhere, right?
Yeah.
Propagate, yeah. Don't know. Cannot think of anything.
Awesome. So I think I'll close the discussion at this point. Maria, I really appreciate we took you for way longer than you expected, I think.
That's fine. Yeah, that's fine. I appreciate the interest. Okay.
No, that is super fascinating, and I think we can do a lot of interesting stuff. We'll also keep you updated about the progress we're doing in what we discussed before.
Yeah. Yes, please. Yeah, and I hope Peter joins, because Peter is very close to me.
Yeah.
Not in the same building, but very close.
So, Michael, you help remind me to send up an email that is bringing up the two questions we had here on the context of harmonic generation and above threshold ionization. To also write it to Peter, whether we can do something with because he's around and he definitely does above threshold ionization in some of his experiments. So maybe that will be a perfect way to try and make that happen pretty soon. So, okay, remind me to
so above threshold ionization and
harmonic generation. Both of those with
using bright squeeze vacuum.
Yeah, with bright squeeze vacuum. And we also write to Peter about this.
Michael, are you from Erlangen, from Peter's group, or why are you the connection between Peter and?
Oh no, I'm just the gopher. No, I'm in Ido's group.
Okay.
I'm the one who's.
Yeah, but we did have a few people who joined us, at least until we started the late discussion, also from Peter's group that I saw connected to the talk. So this will be useful to keep them in the loop. And Raphael is now working on Peter's sample, so we will keep this moving forward for sure.
Great. So, yeah.
Awesome. Thanks everyone for the discussion.
Well, thank you once again. Yeah.
Thanks guys.
Bye.
Bye.
הנה. אוקיי, ליב ולב מיטינג. חברתי.